Okay, there we go. All right, so we left off on Monday with this exercise, which you did something very similar yesterday in your labs, where you have to check basically a range of values. Right? Given a decibel level of 0 to 60, you'll output that it's quiet because that's the level of the noise there. 61 to 70, conversational. 71 to 110, loud. 111 to 194, that's going to be dangerous. And then beyond that, what do we do, right? What about negative values? What about values that exceed the defined values? So we started out here, and I've filled out a little bit more here, that we'll read interactively from the user a decibel level. So when we run this, of course, you'll enter in like 32 or something like that. That's what we did last time. And then we left it off with checking this, checking first for the first level, 0 to 60, and then we'll output that it's quiet. And then we tried to take care of the next level, 61 through 70. Now, as you probably learned in your lab, these need to be mutually exclusive. So it's not okay to separate these out into two independent if statements. Instead, what should we do? If we want exactly one of these things to print, quiet, conversational, loud, dangerous, or other, then we need to make them mutually exclusive. How do we make them mutually exclusive? With an else if statement. So let me go ahead and bring that up here. Great. All right, so I'm going to go ahead and conversational. All right, I'll go ahead and write it completely out there. Let me go ahead and cut and paste and else if. What was it? 71 through 110, 71 through 110. That was dangerous, or was it just loud? Yeah, it's just loud. Sorry, loud. And then another one, 110 up to 111, up to 194, I think it was, and that's going to be dangerous. And then et cetera, et cetera. So I did this intentionally. There's obviously an error here. There are a couple of errors here. What's wrong? I've got double brackets, right? Now, it's okay in this instance because it's a syntax error, but if I had copied a logical error, what I was doing was I was copy-pasting, right? I was copy-pasting code. Anytime you find yourself copy-pasting, changing, and editing code, really rethink what you're doing. Because maybe there's a better way of doing it, or even if this is the way that you do it, like we have a bunch of if-else-if statements here, maybe we want to rethink how we're doing it, because if you've got an error in your original thing that you're copying, and you paste it, copy, paste it, now you've got that same error repeated over and over and over again. We call that copy pasta because it leads to spaghetti code. Remember spaghetti code? Spaghetti is completely unorganized. And you can never tell one noodle from the next. You want your code to be readable, organized, and understandable. So don't copy pasta because it leads to spaghetti code. Let me go ahead and continue with this. So it was 194. Now what? 190. What about 195? What kind of case should I take care of at the end here? The final case. Should I do else if decibel is greater than or equal to 195? Is that necessary to check that? No. All right, maybe not. We'll come back to this. But what should I print? More importantly, what should I do? Print question mark. What should I do? All right. So in the real world, if you've got something that's unspecified, you need to go back to where the stakeholders, the people who are in charge of the project or who own the software product that you're doing or something like that, or basically who have paid for you to develop this thing. And you need to go back and you need to sit down with them and say, well, what happens in this situation? You need to understand the business rules. You need to understand what should happen in each and every circumstance so that you can put that into the specifications. As we had up here, I didn't specify anything. These were incomplete specifications. So with incomplete specifications, we go back to the client and we say, well, what happens in this instance? If we're not able to do that, like for example, right, I'm the client, so I can say what we should do. You make an educated guess. We'll go ahead and print an error message here that error decibel exceeds the limit. Okay? And we'll just say that we don't know how to categorize that because that was not given as part of the specifications. And everybody said that this is not necessary. Why? Why is this not necessary? If it's not between 0 and 60, then it must be between 61 and 70. And if it's not that, then it's not that, it's not that. Then this last one, we can go ahead and leave it off and just be a regular old else, right? All right, I'll go with that for now. Let's go ahead and test this, all right? Let's go ahead and enter a decibel level that we know is quiet, 30 decibels. Right? It's quiet. Right? Let's go ahead and enter a decibel level on one of the ends, so like 70. This should be conversational, right? And it is. Good. What about one of the other things, like, say, 190, just 190? Right? This is dangerous. It is dangerous. Let's go ahead and go with something that goes beyond those limits, 200. Okay? Error decibel level exceeds limits. Okay, so we're all doing just fine so far. What if I go ahead and try -10? What would you expect to happen here? Some sort of an error message because you can't have negative decimals or decibels, right? Let's go ahead and try it. Error exceeds the limit. Does -10 exceed the limit? It's certainly out of the range of what we've got, but does it exceed the limit? No, we get the wrong error message here. Why? Because it falls through, right? It's not between 0 to 60. It's not between 61 and 70. Not. And so by writing our else statement here, that's the alternative to everything. If it's false, 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 the else condition captures any other value, including negative values here. So what should we have done instead? Give me one solution that we can take care of. One way of taking care of this. We could say that we could just say, okay, well, we don't care if it's above or below. The decibel is out of the range or something like that, right? I want to be a little bit more helpful, though. I want to say that it's below the range or it exceeds the range. So I'm going to go ahead and keep that. What if I want to check for whether or not it's less than 0? Right? So all right, I need to take care of that case, right? Where should that case be? Before what? Before anything else? Okay, I'll go with that. If decibel is less than 0, then I'll go ahead and add another case. Let's go with printf decibels cannot be 0, or cannot be negative. There we go. I like that. And now I get a more descriptive error message. End this. Else if, to fix that, and we're good. Right? And now let's go ahead and try it again. -10, and now we get decibels cannot be negative. Of course, we would want to go back and do our ad hoc testing of, did we break anything else? What about 30? Okay, it's still quiet. What about 75? All right, it's still loud, et cetera, et cetera. I'm doing ad hoc testing here. And you saw a preview of why you don't want to do this, because if you ever make a change, you have to go back and do all your testing over again. Ever make another change, you have to go back and do all your testing again, right? That kind of testing is really brittle. That's why in Lab 3 yesterday, we kind of gave you a preview of what unit testing looks like. That you write code to test other code so that you can automate all those tests, that you can go ahead and just run this button over here so that you can test everything. You also see this as a preview in your first assignment, which is due this Friday, right? You have to fix several errors in this Capricar project. Well, we've got ad hoc testing where you've got this Capricar demo that you can run a single test there, a single test there. But then we've also got this ad hoc automated testing where it runs through thousands of test cases at once and reports back that you passed 500 of them, you failed the other 500. Right? And then we've got a more formal testing framework, CMACA. Don't worry about getting into the nitty-gritty details of how those things work. We'll save that for later. The focus of that first assignment is for you to just get some more Git experience. Okay? You could also simplify this greatly, right? So let's take a look at this logic here. Right? If you can simplify code, you do it. Right? The KISS principle. Keep it simple, stupid. If this first one is not true, what do we know? What if we get to line 13 without this having run? What do we know about the decibel level? That it's non-negative, right? It could be 0 technically, right? So do I need to check that it's greater than or equal to 0 again? No. I could go ahead and simplify this. And I'll show you that it leads to the exact same thing here. Negative 10 is still going to be, you cannot do that. And 30 is still going to be quiet. Right? And I can simplify this all throughout. I don't need the lower bound checks on any of this stuff anymore. Right? And that's much simpler code. But it only works because I'm going in order. Remember, if-else-if statements, the first one that evaluates to true is the one that gets executed. If I had done my negative check down here instead, well, then this wouldn't have worked, right? If I had done my else-if negative down here, then negative 10, well, that's certainly less than or equal to 60, so it would have said that negative 10 is actually quiet. And that's not what I want, okay? All right, this looks pretty good and as simple as it's going to get. So I'll go ahead and cut and paste this and put it in the notes so that you have it when I update it tonight, okay? All right, one last thing with respect to conditionals is something called short-circuiting. I think that's spelled correctly. Yep, that is. All right. So what is short-circuiting with respect to electrical circuits? All right, we've got several EE people out there. If I've got a circuit here, here's a battery and here's a light bulb. Positive charge is going this way, and then negative charge, I think it goes that way, right? Positive goes out, positive in negative. Is that right? EE people? Okay, thank you. If I've got this large circuit here, what is short-circuiting it? Take a wire and put it in the middle over here, and take and connect the other end of the wire over here. I've shortened the circuit. Is the light bulb going to light up anymore? Is it? EE people? No. Why? Because now where is the electricity flowing? It's going up here and then taking my short circuit and then going back, right? I've shortened the circuit. And now, because electricity always wants to take the path of least resistance. If it's got a shorter circuit, a shorter cycle to travel, then it does it, right? Short-circuiting with respect to logical statements works very, very similar. If you can get away without doing work, a program does it, right? Because it saves on energy, it saves on CPU cycles, it saves on time. So what I mean by that is consider the following logical statement, right? So A and B, right? Now suppose, let's just go over 2. Suppose that A evaluates to true. Right? Does it matter what the value of B is? Right? Or what I meant is false. There we go. False. There we go. Following. All right. So I've got A. What is the ampersand again? And A and B, which is true if only if and only if both of them are going to be true. But suppose that A, the first one, evaluates to false. Does it matter what the second one is? It could be true. It could be false. It doesn't matter what it is because the entire thing is going to be false. So the answer is no. No. The first being false makes the entire expression false. Right? So consequently, C and the vast majority of programming languages will not evaluate B. Right? Its evaluation is skipped, or again, where do we get this term? Short-circuited. Right? It's not going to evaluate that at all. Now, it doesn't matter that much if this is a Boolean variable, but when we get to other certain things like function calls, if B were a function call or an expression, or like B squared minus 4AC, that would not even get evaluated because that costs CPU cycles. It costs to multiply once, twice, thrice, and then take a difference of those stuff. So if you can skip that work, then a program will. Now, you're only skipping a few CPU cycles, so you're not even going to notice it in the grand scheme of things. But think back 40, 50 years when CPU cycles were measured in milliseconds even, or you only had a few CPU cycles per second, right? If you could save a few CPU cycles, you did it, because it sped things up so much. And now it's become expected, right? So it was originally done to save on CPU cycles time, right, and efficiency. Not so much of an issue anymore since computers are super fast, but of course it's still, if you can do things more efficiently, you still do it. But it is still used in languages because it is familiar, right? It has become a common programming idiom, right? So what is an idiom in plain old English? It's a colloquial metaphor, right? So forget about the definition of an idiom. Give me an example. Does anybody have an example? Exactly, the raining cats and dogs, right? Literally, that makes no sense. And if you were to translate that to another language where they don't have that idiom, then they would, what the hell are you trying to say, right? It would not make much sense. Just taking it literally that cats and dogs are raining down from the sky, it doesn't make any sense because it has a certain context. In English, in American English, I don't even know if like British would understand what we're talking about, or if that's an idiom in other languages. But even English in different countries and different regions differs. You might have a regional idiom that people outside that region don't understand, right, unless you explain it to them. And so it's in the context of programming languages, we also have idioms. We have common patterns that don't necessarily have a literal meaning, but that everybody has an understanding of what they mean after they've been programming long enough. Short-circuiting is one of those idioms. People will often write code knowing about short-circuiting and knowing I'll do a check to see if I'm about to divide by 0 or something. And if I'm trying to, we haven't got to null pointers yet, but I'll do a check to see if this is a valid thing, and then I'll check its value, right? This thing over here is going to be dangerous. So what I do is I put my check and my dangerous operation in a logical statement like that, and then I know that I can rely on short-circuiting so that this dangerous statement, if this is false, that's not going to get executed over there. It allows me to prevent errors and runtime errors, and we'll see why later on when we get to null pointers. Okay? But it's become a common programming idiom. Likewise, with the OR operation, consider the following logical statement. If I've got A or B, then same question. Suppose that A evaluates to true in this case. Does it matter what the value of B is? No, why? It could be true or it could be false. At least one of those operands needs to be true, and the entire thing is true. If the first is true, then the entire expression is true, regardless of the value of B. Right? So we don't need to take care of that, or we don't need to examine B, and consequently it short circuits and it doesn't even evaluate B. Again, it could be that B is an entire expression that gets skipped and several CPU cycles are saved. It could be a dangerous expression that could cause a runtime error if the first one was not true or false, depending on what you're trying to do. Right? It's common programming idioms. Okay? And it's called short-circuiting. The vast majority of programming languages support it. Why? Because the first programming languages supported it. And it's become, because it's an idiom, people come to expect it. If you were to design a brand new programming language that did not have short-circuiting, that would throw everybody for a loop. Right? And it's just because it's been established for so long that it needs to be continued to be established like this. Okay? All right. So any questions so far? Okay. Then what I wanted to do is I wanted to remind you of a few of the pitfalls that we looked at last time. So one of the pitfalls that we had was if we don't properly use the AND connective, right? If I were to do something like this, if A, what I'm trying to do is I'm trying to check to see if it's in a range of 0 to 10 inclusive on both ends. But this is not going to work because of the way that C evaluates stuff. It'll evaluate the 0 less than or equal to A. That has a truth value. It's either 0 or 1 or something, which is always going to be less than 10. Similarly, another pitfall that we had was not using the equality testing operator equals, and instead putting a single equals sign here. Right? Now, I've got an example set up here. Don't worry about the name just yet. With a whole bunch of those type of errors intentionally placed into this program. Now, this program doesn't do anything other than a little bit of mathematics. It prints it out. Please enter a number. It reads that number, and you can see immediately that there's that bad pitfall, right? And there's that bad first pitfall that I was talking about. Let me go ahead. I'm on CSE now. Let me go ahead and compile this thing. GCC says no news is good news, right? There were no compilation errors, right? It will compile, it'll run, but it won't give us the correct results. Let me go ahead and show you that I'll run this. It prompts me for a number 123, segmentation fault, right? Not only that, but it's going to give me, even if I get past that error, it's still going to give me a whole bunch of errors. But everything compiled, right? There's no problem with it. There's no syntax errors with it. So one tool that you can use to detect these kind of things is called a linter. Right? So let's talk about linters. First of all, what is a lint? What is lint? Again, let's think about plain old English. Like I said before, there's an old adage in computer science. There's only two difficult things in computer science: cache invalidation and naming things. So usually when we try to name a concept in computer science, we just think about the real world and what's kind of the analog to it. What analogy can we draw? And we're just going to borrow that language. So let's think about the real world. Let's think about lint. What is lint? It's the stuff on your clothes, right? You put your clothes into the washer. They get washed. You put them into the dryer. They come out of the dryer. Lots of the lint has been taken off from the dryer, but there might still be a little piece of lint on there. Does that mean that your clothes are dirty? No. It just means that you've got a little bit of lint. If it's just a T-shirt, you put it on, you don't care, you walk out the door. If it's a nice suit or something like that, then what do you do to clean it? You don't want. It doesn't mean that it's dirty, but if you're going to go out to a more formal thing, to a wedding or something, and it's a black tie affair, do you want lint all over your nice black suit? No. So what do? You take a lint. What do they call them? A lint roller, and it's just a sticky thing that takes off all the lint. Right? So lint is not necessarily something that's bad, unless you want to be absolutely sure that you're going to look your best at that black tie affair, right? So in the context of code, lint is often suspicious. Let me rewrite it like this. Code may be syntactically correct. That is, it will compile, but still may have errors, right? Lint are pieces of code that may look suspicious. Suspicious. All right. Oh, hey, no. I don't have a spell checker on here. Fine. Whatever. Suspicious. I don't know how to spell it. No, that's not right either. All right. Whatever it is. Oh, hey, there. I got it. Finally. Lint are pieces of code that may look suspicious and may lead to errors, but are not syntax errors. All right? And they might look suspicious, and they might even be false positives. In other words, this looks suspicious, but actually that's what you meant to do. Right? Yeah, I know what I'm doing. I meant to put that lint there. I'm only wearing the T-shirt. I'm not wearing the tuxedo out tonight. It's okay if we've got that lint there. Right? Linters are static analysis tools that look for such potential errors in your code and report them, usually as warnings. All right? So what is static analysis? It's just any program, a program that analyzes the source code of another program pre-compilation. We also have what are called dynamic analyzers, which actually analyze a program as it's running. We'll talk about that much later. Forget the one that that I'll show you, but it's used to detect memory leaks when we get to memory eventually. But static analysis are it's an entire area of tools that you can use to look at your code and say, well, this is syntactically correct, but you probably didn't mean to do that because it's going to lead to this kind of this type of error, right? And you can program your own static analyzers and linters to look for certain things, look for common bad patterns in your code. We have a static analyzer with respect to GCC. GCC, your compiler, can be used as a rudimentary static and linter, I'll say, linter, using the flag WAL or wall, right? We call that the wall flag, but it actually does not stand for a wall. The first W stands for warnings, and the ALL stands for all of them. Print all of the warnings because I want to make absolutely sure that my code is correct, okay? So let me go ahead and demonstrate that with the code that we just looked at, right? Now you might be able to look, you might be able to look through this code, and if you've got eagle eyes and you can look through this code and see exactly what's wrong, I can point those things out to you to exactly what's wrong, or we can rely on GCC to tell us these things. If you don't have that flag there, you don't get anything reported, because by default, at least on CSE, all the warnings are shut off. So what I'm going to do is I'm going to turn on all the warnings using the warnings all or wall flag. Right? And when I do that, wow, it found a lot of stuff that's suspicious. Right? These are not syntax errors. This is perfectly valid, syntactically valid C. But you can see that there's a lot of problems here. Let's start at the top. Again, they're all warnings. Format %f expects a matching double argument. So on line 12, column 3, what are we doing here? Let's go ahead and open up the code. Copy lint example to lint example backup. I don't want to lose the original. Right. There we go. All right, let's take a look at this. Line 12, there's line 12. What are we doing here? Or what are we not doing here? We're printing out the value of C, which is a %f. Well, C is a double, right? It's being output. What did I forget, though? I needed to put the actual variable there, right? And GCC caught that because I was running with all the warnings on there. Let's go ahead and run it again and see if we've cut down on the number of warnings here. But now there's a warning on line 15. Format %d expects type int star. We don't know what that means yet. But argument of type 2 is int. Right? Just by looking at it now that you know that there's a problem on this line, tell me what the problem is. An ampersand. I forgot my ampersand. So let's go back over here, put my ampersand in, and now that warning is taken care of. The next warning on line 17, there's that classic pitfall that I was telling you about. And now it was not a syntax error before, but now by running with the WAL flag, I get a report that, is that really what you meant to do? Right? And is it really what I meant to do? No. So let me go ahead and run it and show you that now taking care of that ampersand will take care of the actual problem. But of course, did you read 0? No. You read 123. Is 123 in this range? No. Right? And that's because of these two warnings. Here's the first warning. You probably meant equals equals. Here's the second warning. Comparisons like x, y, z do not have a mathematical meaning. Right? It does not have a mathematical meaning. Why? How should I have done that instead? I need to break it up into 2 checks. When I do that, GCC. Oh, I still have 1 warning, but we'll go ahead and take care of those in 2 warnings. I'll take care of those in a second here. Now 1, 2, 3. I read 123. That's solved. And it's not in the range of 0 to 10. That's solved. Let's go ahead and compile it one more time and see what else we've screwed up here. Warning, return with no value and function returning a non-void. What does that mean? On line 31, I have a return statement, but what should I be returning? An integer. So I should be returning, in this case, everything was fine, no errors, so 0. And finally, the last one is just a stylistic thing. Warning, unused variable y on line 7. Let's take a look at line 7. I declared the variable y. Did I ever use it? No. So if you didn't use it, you declared it, why is it still there? Take care of it. We call that what? Dead or unused code should be removed. What do we call that again? Cruft, right? We want to take care of that, and we don't want to have dead or unused code there. We want to take care of all of our compiler warnings. And now I have a much cleaner program. It's a black tie affair. It is a tuxedo. I wanted to take that lint roller and clean it all up. Right? It was clean code syntactically, but now it's super clean code, and we're ready. Right? Always do that. So from now on, now that I've showed you this, always run with the WAL flag so that you can take care of those things and not rack your brains thinking, what's going on here? Where's the error? I can't find it because it seg faults out. I forgot the ampersand on line 22, and it'll tell you right there. All right? Okay. So always run, in general, or it's best practice to always compile with this flag. All right? Take care of all your compiler warnings. Some of them you won't be able to take care of because, again, sometimes you do want lint. Right? Yes, that's actually what I meant. And if, in a lot of projects, if you know what you're doing, and yes, I know that that looks suspicious, but that's how I'm doing it because it's a hack and it needs to be done that way. You can configure your build system. You used make the other day, or you are using it on your assignment 1. You can configure your build system to suppress those specific warnings so it doesn't show up at all. Right? Okay. All right, those are linters. All right. Let's see. What else do I want? Let's go with this. There we go. All right. I will go ahead and post that later today. Next week we'll be starting on Module 4. So I'm going to give you a preview with the rest of the remaining time here. And our next topic is loops. Now that we've got basic input, output, basic variables, we've got conditions, do this or do that, or do this, not do that, or do one of these 3 or 4 or 5 things, but not the others. We need a way of repeating code, right? We need a way to repeat, like take a block of code and execute it over and over and over again until some condition is satisfied or until some condition is not satisfied. If you typically want to do this is if you've got 200 students in a class. You don't want to take the code to compute student 1's grade and then cut, paste, cut, paste, cut, paste. Why? You don't want to do copy pasta. Instead, you want to write one piece of code that will compute a grade and then run that piece of code 200 times, once for each student, right? Because, of course, you can't predict that this system will only ever have 200 students. Sometimes it'll have 100. Sometimes it'll have 250. Sometimes it'll have 1. You don't want to have to write a bunch of conditional code, and I've seen people do that before, even in production systems, for whatever reason. But instead, you want to write one good piece of code and then loop it as many times as you need. There are 3 basic elements to any loop control structure, repeating things over and over again. If you are going to repeat things over and over again, first of all, you need a starting point. Where do you start? Right? Then you also need to determine whether or not you continue around the loop. So if I start on the track, right, I've run a distance of 0. Go around the track, say it's a mile track, and I've run a distance of 1 mile. Run around it again, 2 miles, 3 miles, 4 miles. When do you stop? Right? Do I just keep running until I die? No, you want to run. I wanted to run 5 miles today. So I'll go ahead and run, and I know that I should stop after I've run 5 miles. So you need a beginning point. You need a stopping point, or a condition that tells you that you should keep going because you have not run yet 5 miles. And then, of course, you need a way to work from that starting point to that endpoint, that termination condition. And the way that you do that is by keeping count. I've run 1 mile. I've run 2 miles. I've run 3 miles, 4 miles, and 5 miles. Now I'm done. Right? So there are 3 aspects to each loop. And I would add maybe a 4th aspect. Another aspect is the loop body. Right? What you actually do on each, we call these iterations. So each time you go around the loop is an iteration. Iteration 1, iteration 2, iteration 3. Okay? So there are several loop control structures. We're going to focus on just 2 of them, 2 of the most useful ones. For loops. Right? That's the first one that we'll take a look at here. Right? A for loop, guess which keyword it uses? Keyword for, exactly. Right? It uses the keyword for. All 3 elements, that is the initialization, continuation, and increment, right, are all located on the same line. For loops are very easy to read because you have all 3 elements right on one line, one after the other. This is where you begin. This is the condition that you continue on, and then this is how you get there. Right? Let me go ahead and just give you a concrete example to start out with. I'll go ahead and say int I, no, I'll go ahead and go the modern way. For int I equals 0, or let's go with, we'll count 1 to 10. I is less than or equal to 10, I plus plus. Right? And I'll talk about each one of these elements here in a second here. But printf percent I is now equal to %d and the line I. Let me take this for loop and bring it over to REPL, and let's actually let's see its execution. Right? So I don't want to get rid of all of this. I just want to get rid of this part. There we go. All right. This loop that I just designed is simply going to count to 10. Here's the increment. Here's the initialization condition. We'll start I at value 1. Right? So we're running the first mile here. Now this is going to be a 10 mile. Let's say K instead. I don't want to run 10 miles. I'll run 10K instead. I'll start at 1. Then, while I is less than or equal to 10, run this loop. At the end of this loop, make a progress towards your termination condition of 10 by this is a syntactic sure here. You add 1 to I. Let me go ahead and run this and show you what it's going to actually run. It's going to run 1, 2, 3, 4. What's the last thing it's going to print? 10. Right? 1, 2, 3, 4. Of course, it's printing I is equal to these things. Right? Nope, I don't want a new version. Okay. There's our first basic for loop. Again, this is the initialization condition. This is the continuation condition. While this is true, I will continue to execute the loop. And then this here is my increment condition that is executed at the end of the loop. So let's codify all that. The initialization statement creates and initializes a variable I to 1. Right? Oops, just 1. The initialization is this following statement here. Int I is equal to 1. Right? And note that it ends with a semicolon. Why? Because it's a statement. Right? The second part here, I is less than or equal to 10, is the continuation statement. While this statement evaluates to true, the loop will execute again. Right? One more iteration. Right? Then the last one is I++, is the increment statement. The statement that makes progress towards the termination condition. The termination condition is nothing more than the negation of the continuation condition. While this is true, continue. The moment that it becomes false, stop. Right? And that's what you're doing with this loop. Yeah, way back there.
So the first thing, or sorry, the last part that you put
Yes?
You feel like it would make more sense for that to be within the brackets. That way it'll repeat every time it runs rather than putting it there.
Hold on to that thought for a second. All right. I'll add two things to that, right? And I'll put them under subheadings here. The increment is automatically executed at the end of the loop, right? That's just the syntax. That's the understanding. That this increment is going to increment at the end of the loop. Let's go back to the REPL here. If it executed at the beginning of the loop, you would get completely different behavior. You would actually we started it at 1. If this executed right away, then 1 plus 1, well, that's going to be 2. And it would have started right here instead. Right? So this is always going to execute at the end of the statement. It's kind of like putting it down here instead. And this is actually valid syntax. But we like using for loops because we can put all three of those things up at the top here. Okay? Yeah? Let's go ahead and try. So I'll start I at 1 while it's less than 10, less than or equal to negative 10. Is it? Is 1 less than or equal to negative 10? So what should this print? Absolutely nothing. Right? It says it starts at 1. It's not true, so it doesn't execute at all. And normal control flow returns to line 9 here. Right? So no execution at all. Loops don't have to execute. Right? It depends on how you write them. Okay? The other thing that I would mention is the increment uses the increment operator, plus plus. Right? So this is simply syntactic sugar. What is syntactic sugar? So what is sugar? Is sugar good for you? It's not. No, it's not great for you. But is it bad for you necessarily? Not necessarily. Right? As long as you don't eat too much sugar, right? It's not necessarily bad for you. But we call it syntactic sugar because it adds flavor. Maybe you want to call it syntactic salt, but that's not a great metaphor. It adds flavor to your language. Think about English, right? Think about all of the adjectives that we have that you can describe. Pull out your thesaurus, and you can find 100 different words that mean the same thing. Good, right? Good, excellent, outstanding, right? All those things mean the same thing. But we have a lot of why do we have so many different words to describe the same thing? Because it adds flavor to our language, right? We can use them in different contexts to convey different meanings. Likewise, we like our programming languages to have syntactic sugar. Different ways of doing things, more compact ways of doing things. It provides an easier, shorter way to simply add 1 to a variable, right? We could, you could just do equivalently. You could have done I is equal to I plus 1, right? And, that's clear. Everybody would understand what you're doing. But I plus plus is so much shorter, right? And that's what they added that syntactic sugar way back when. Most programming languages support it. I put the equivalent into quotes there because it's not actually equivalent. This is one operator, and I'll go ahead and put the I here. This is one operator. This is actually two operators. I plus 1 is one addition, and then this is an actual assignment. Right? This is one operator instead. So it's equivalent in that it leads to the same thing, but it is not equivalent in that as a technicality. Right? But it's a nicer, more compact way of writing things. If you just want to add 1, then you just go I plus plus. Others. So what if you just wanted to subtract 1? What do you think you would do? I minus minus. Oops, there we go. This subtracts 1 from I. What if you wanted to do other increments? What if you wanted to go by 2s? I want to go 0, 2, 4, 6, 8. Right? I want to count up by 2s. How could I do that? Plus equals 2. Right? This is equivalent to I is equal to I plus 2. Right? If you just want to add 2 to it, you can go plus equals 2. And that'll add 2, 4, 6, 8, et cetera, et cetera. Well, if you can do that with plus, you can also do that with minus. I minus equals, say, 5 would subtract 5 from I, right? Compactly. And it would be more verbosely written as I is equal to I minus 5. Right? Well, if you can do it with plus and minus, you can also do it with, what other operators do you think you could do it with? Multiplication. I times equals 2. So this multiplies by 2. Right? And you can also do it with division. I divided by equals 10. This divides by 10. Right? And those don't have to be hard-coded literal values, 10, 2, 5. Those could be other variables if you wanted, or an entire expression. Just make sure to put them into parentheses for readability. Okay? It's all syntactic sugar. It's more compact, shorter ways of writing things. And once you get used to them, once you understand them, it's quicker to read them and understand them. Okay? Plus, plus, minus, minus, those are going to be your bread and butter all over. Right? So that is a basic for loop. Right? So let's talk a little bit about scope. Scope. Right? So recall, what is a variable scope? Remember? So recall that. Did I go over 1, 2? There we go. 2. There. The scope of a variable is the section of code in which it exists. Right? It is visible. Right? That's why we call it the scope, because if you look through a scope, you can only see part of your world. And so if you don't have a scope, then you see the entire world at once. Right? And you want to limit the scope of a variable as much as possible. In general, it is best to limit the scope of a variable to the as much as possible. Right? So with respect to loops, declaring, that is creating, an index variable, index increment variable, inside the loop will limit its scope to that loop and not beyond. Okay? Now what I mean by that is, let's go ahead and go back over to our code here, and let's go ahead and try to print I again. I is now %d, end of line, I. Right? And immediately you're going to see that there's a problem. Right? There's a little red squiggly line under there. That's not the passive-aggressive one. By the way, remember I called those the green squiggly lines the passive-aggressive ones? Those were the warnings that you get out of GCC when you turn on the WAL flag. Right? This is on by default. But this is actually a syntax error. In fact, let's go ahead and hover over it and find out what kind of syntax error. Use of undeclared identifier I. In other words, you didn't declare I. Yeah, I did. I declared it on line 6, right? But I declared it inside of the loop. So what is its scope? It's limited to that loop. It's the variable I only exists as far as the lifespan of this loop right here. It exists for lines 6 through 8. After that and before that, it no longer exists. Right? I could change that by doing old school C here. I'll go ahead and declare my variable outside, and now I'll take care of this. Right? There. Now it goes away. Guess, or make a prediction here on what value is going to be printed on this line here. So I was 1, then 2, then 3, 4, 5, 6, 7, 8, 9, 10. 10 was printed before, right? Because while I is less than or equal to 10, go through the loop on line 8 and print it out. So it printed 10. Now we're outside the loop. What value does I have now? It could be garbage, maybe. It could be 0. Oh, let's find out. I is now 11. Why? Remember, I increased the scope. Before I was looking at this little tiny scope, and now I'm looking at a much larger scope. I exist before, and it exists after. How did I get out of the loop? I counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What got me out of the loop, though? Going up to, and I've run out of fingers, so 11. Right? At the last iteration of this loop, it got up to 10, and then at the end of that iteration, it added one more, 11. And that's what got me out of this loop, because 11 is no longer less than or equal to 10. It retained that value on line 11 there. It's just coincidence, right? And that's why it printed out that I is now 11, okay? In general, you don't want to do this. Right? In general, you want to limit the scope of your variables as much as possible. And so this, I've increased the scope of I. It exists before, it exists after. If I've got another 100 lines of code after this loop, I still exists. And you can't, you can reuse it if you want to, but otherwise you've made your code more brittle. You've introduced a potential failure point. What if you forget that you created this variable I and then you want to use another variable called I? Well, you can't do that because it was already created up there, et cetera, et cetera. So limit your scope of variables. Limit it to that particular loop. Right? And of course, now it doesn't exist at all. If I tried to print it out, of course, it won't even compile. It'll say you can't do that. I don't know anything about I, because I exists only for lines 6 through 8. Okay? So, in general, you want to limit the scope of your variables. Yeah?
Can you use the value that you get from a for loop and declare into another variable, like outside the for loop?
Yes. For example, let's go ahead and declare I again. Int I is equal to 42. And let's restore this.
No, but I mean, to get an answer for your for loop, you can use that answer for your for loop to declare another variable outside the for loop.
If you store it off into a variable, right? So I could say int x is equal to I plus 10, right? Now, if I declare it here, is it going to exist over here? This is an excellent question on scoping. X is now this, except that, whoa, what's wrong? It's not going to let me do that because where did you declare it? You declared it inside the loop. Its scope is limited to that loop. If you want it after the loop, you have to declare it before, int x. Right? Now, get rid of this. Now it exists. And I don't, here, another prediction. What value will it have? This is a good test question or something. I don't know. So on the last iteration, I was 10. So 10 plus 10 is going to be 20. Then I gets incremented to 11, breaking us out of the for loop. Did I update the value of x? So I think it's going to be 20. And it was. All right. Okay. So good question. Does that answer it? Okay, great. And I'll keep that later for the notes there. So with respect to loops, you want to limit the scope of variables as much as possible. Note, or caveat emptor, however you spell that, right? Buyer beware. For old school C, you cannot declare a loop variable. You cannot declare a loop variable that is inside the loop. Right? So what do I mean by that? Let's take this perfectly fine C code that was running on REPL, and let's take it to the CSE command line. foo.c. Okay, I'm going to have to copy the entire thing now. Copy it, paste. There we go. Let's go ahead and try to compile that same exact code from the CSE command line. It doesn't like it. Why? For loop initialization declarations are only allowed in C99. What do you think that 99 stands for? 1999, right? C is a pretty old language. 79, I think it came out. It was ANSI C. And then it was ratified and codified into a standard. C89 was the first official standard. And then every 10 years since, it's been updated. There's C99 about every 10 years. It's been updated since. I think that there was a C11 is the most current. And then, of course, maybe in the next year or two, they'll have C20 or something like that. Way back when, C89 and before, they didn't allow you to do something like this. They did not allow you to declare a loop variable inside the loop. This was a feature that was added to later versions of C. I want to be able to use this. So I'm going to go ahead and take GCC's advice here and change, this is the one I would recommend, and change the standard. STD is going to be standard. Do you want to be the standard with 1979C or 1989C or 1999C or some future version that's in beta, right? Which one do you want to be to standardize to? I'm going to go ahead and go with C99, right? The vast majority of stuff that you're going to do in this class will not require anything from C11 at all. C11, mostly, most of the updates were done internally. So I'll go ahead and put this flag, and I will compile the same file, and now it's happy. Right? It's happy because I said I want to compile this C code under the C1999 standard. Right? It's actually the GNU 99 standard, which has a bunch of other things added in, but it doesn't really matter. So from now on, when you compile, you should use this flag as well. Use all the flags, right? And I'll go ahead and post, if anybody's interested, I can post later on Piazza about how you can get this automatically by making an alias, okay? So to compile under a more modern standard on CSE, use the STD flag, right? And here's the example that I just did, okay? Later on, better yet, you can define an alias so you don't have to type it all the time, right? See Piazza. And hopefully somebody will remind me, and I'll go ahead and post that later on, right? Because I don't remember how to do an alias off the top of my head safely. Actually, it's going to take some hacking of a bash file or something. I don't know. But anyway, that's why I'm not going to do it as part of the class today. All right? I'll post it later, okay? All right, so, yep, there we go. Let's do a really quick exercise. Another example. All right. Oops. Let's go ahead and develop the C code over here, and then we'll take it over to REPL to see if it works. Write a loop to print out numbers 10 to 100, but 1 per line. And by increments of 10. Right? Actually, no, let's split this up into 2 loops and do it 2 different ways. So all of the numbers, 10 up to 100, and then we'll go 10, 20, 30, 40, all the way up to 100. So help me out. Let's write a for loop here. In fact, I don't like this highlighting. Let's go ahead and just go over to REPL right away. There we go. Write a loop to print out the numbers 10 to 100, 1 to a line. So help me out. Let's write this as a for loop. Int I is good enough. By the way, why do we use I? Because if we've got other loops, we use IJK. I stands for index, increment, right? It's a good place to start. If you're using X, that kind of tells me that it's kind of like a Cartesian product, like the Cartesian plane XY, XYZ. Probably not good index variables. If you start with A, B, C, that's also, you know, there's some established math that uses that kind of stuff. But IJK, those are the bread and butter of for loops. So it's perfectly fine. It's normal. It's idiomatic. It's an idiom to use all those, to use I, J, and K. Where should I start? Should I start at 0, or should I start at 1 like I did before? Nope. If I want to print 10 to 100, where should I start? 10. I is less than 100? Less than or equal to, because I want to include 100 on my last iteration. And I'll go I++ for this first version. Printf, I is equal to %d and the line, I. Right? And let's go ahead and run this and see how it works. And yep, 10, 11, 12, 13, all blah, blah, blah. And you can't see this, and there's no way to get rid of it. But I'm sure that there's 100 underneath. Right? Okay. Second version. Let's go up by increments of 10. How could I do that very, very easily? Instead of going up by increments of 1, plus, or I could go with I is equal to I plus 10, except for I've got some shortened syntactic sugar that allows me to write this a little bit more compactly. Let's go ahead and run it, and you'll see 10, 20, 30, 40, 50, and it goes up to 100. But I can shorten this up how again? Plus equals 10. And some people like to put in more white space to make it more readable. Again, as long as you are being consistent about it. If you're putting white space around all your operands, fine, put it around all of your operands. If you don't have any white space or around your operators, then there shouldn't be any white space anywhere else. This is one I would actually prefer personally, because too much white space can be distracting. Okay, and that works perfectly fine. You know what? Fine. Let's just get rid of that thing. There. Restore. Okay. Now you can see it. 10, 20, 30, 40, all the way up to 100. What if I did strictly less than 100? What's the last thing that's going to get printed? 90. After the iteration is over, I has a value of 100, right? Because it has 90 and then plus 10 to get me up to 100, but that's what breaks me out of this loop. So there's a big difference between less than and less than or equal to. Usually you call those off by 1 errors. Okay? All right. So those are for loops. There's another type of loop called a while loop. Right? There's also do-while loops, and in some languages you've got for each loops, but we're not going to cover either one of those because C does not support the for each loops, and do-while loops are just while loops hidden in disguise, but are much more brittle. Right? So while loops have a slightly different syntax. Right? Syntax. They use the keyword, guess what? While, right? Now, I was reading that for loop in plain English. When I read that for loop, I said, for I equals to 0, while I is less than or equal to 100, right? I used that keyword there when I was reading the loop, but you don't actually use the keyword while in a for loop. You use it in a while loop instead. And the biggest difference, the main difference, is that all three elements, that is the initialization, continuation, and increment, are separated. Right? Okay. So here's the same example of counting from 1 to 10, but using a while loop instead. Here I do have to create a variable outside the loop before it starts, and I will also initialize it to 1. While some condition continue. Right? While I is less than or equal to 10, I will go ahead and print it out. I is equal to %d and the line I. And I have to manually increment I at the end. Okay? So there's a basic while loop. Let's take it over here and look at it, see how it actually runs. There we go. And let's run it. And it does the exact same thing as before. So you might ask yourself initially, well, why do we need 2 loop control structures when I can do the same exact thing, right? And what would your answer be? How do you make food taste better? With? How do you make your cornflakes taste better, at least? Sugar, exactly. This is syntactic sugar. Yes, any while loop can be rewritten as a for loop. Any for loop can be rewritten as a while loop. We like having that variety there because of certain situations. And we'll talk more next time about when one is more naturally appropriate than the other. But for now, let's go ahead and finish up with the behavior of a while loop. Okay? So this is the initialization. The initialization comes before the beginning of the loop. The continuation condition is placed placed next to the while keyword, and the increment is done somewhere inside the loop. Right? If we did it outside the loop, of course, we would get into what's called an infinite loop, and I'll demonstrate that in a second here. Okay? So the increment is done somewhere inside the loop. Now, over here, I chose to do it at the end because I wanted to start at 1, print it, then increment it. 2, print it, increment it. 3. print it, increment it, print it, increment it, print it, increment it. I wanted to increment it afterwards. What if I screwed up, or what if I wanted to do something different and I wanted it incremented before? What's this going to print now? Ignore what's over here already. So walk through the loop here. It's initialized to 1. While I is less than or equal to 10, it is less than or equal to 10. Increment it. Now it has a value of 2. So what gets printed first? 2. What gets printed last? 11? Anybody for 10? 9? 12? 42? Let's find out. So we're all agreed that it starts at 2. And those who said 11 were right. Why? So it comes up 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10. It comes back up to the top. I is less than or equal to 10. But then it gets incremented before it gets printed. So 10 goes to 11, and I've run out of fingers again. And then that's what gets printed. Then it goes up to, the top again. It's still 11, and that's what breaks me out of the loop. So where you do your increment condition matters. If you need to do it at the top for for alternative logic, that's perfectly fine. If you need to do it somewhere in the middle, that's perfectly fine as well. If you need to update it by different increments, that's fine too. You just have to make sure that you're not off by 1. Here I'm off by 1. If my purpose of writing this program was to count from 1 to 10, I've certainly not achieved that. I'm off by 1 iteration. I need to correct that by putting the increment where it should be. Right? In fact, here's a good question. What happened? And these are kind of the gotcha questions in coding interviews. What does this actually print out? No, you don't have a computer in front of you to actually run this. So what does this print out? Let's walk through it. I is 1. It's less than or equal to 10. So it increments to 2. Gets printed. Write that down in your copybook there. 2. Then it gets incremented again at the end of the loop. We come up to the while loop at the top. It's less than or equal to 10. 3. The first thing we do is increment it. 4. Then it gets printed. So what have we printed so far? 2, 4. It gets incremented again. 5. Right? 2, 4, 6, 8. There's going to be a pattern there. What's the last thing that gets printed? What do you think? 10? All right. You passed your interview. Those are the kind of gotcha questions there. Right? You just have to know how loops work and be able to walk through a very, very simple loop. Okay. All right. So those are the basic differences. Yeah, I'll do that later. So let's do some we've got about 5 minutes here. Let's do some common pitfalls. All right. So misplacing a semicolon. Remember misplacing a semicolon with respect to. Oh yeah, go ahead. Well, for C there's do while loops, but we're not going to cover them. I generally don't cover do while loop. The only difference with a do while loop is that it's unconditionally executed the first time, regardless of the continuation condition. The continuation condition is checked at the end of the loop instead of the beginning of the loop. And so if you need to do something in order to set the loop up and then determine, do I need to repeat this or not? Again, it's slightly different than a while loop. You can achieve the same thing with a regular old while loop. And unfortunately, it's a little bit brittle because you have to remember that the continuation condition is evaluated at the end instead, and then there's this extra semicolon that's not present with either of the other two loops. Right? But it is in the book if you're interested in reading about it, a do while loop. And then there's also a for each loop that's not supported by C. If you've got like an array or a collection of all items, lots of languages have syntactic sugar that allow you to iterate over those items without having to write an explicit loop. Right? So misplacing a semicolon. Consider the following code. Right? Let me go ahead and bring this over here and modify it. I++. There we go. Semicolon, semicolon. All right? There. What's wrong with this code? There's a misplaced semicolon somewhere, right? All right, predict what's going to happen here. Nothing's going to be executed? Why do you say that? Yeah, while I is less than 10, what is this doing? It starts at 0, and so it's a little bit different from what we've been doing. Starts at 0 while I is strictly less than 10. Then go ahead and print it I++. But is that actually part of the loop? Is this the loop body right here? Nope. What's the loop body? It's empty. While the way that you actually read this is while I is less than 10, do nothing. I is less than 10, do nothing. I is less than 10, do nothing. We're caught in our loop here, right? Note that it is still running. You just can't see it because it's not doing anything. It's going do nothing, do nothing, do nothing, do nothing. I'm not executing this body down here, so I'm not making progress towards my termination condition. I never reaches 10 because you don't actually print anything. You don't actually increment anything. You have an empty loop body here. This seems familiar, right? This is exactly one of the pitfalls with if conditions. If, and then you put a semicolon there. If whatever condition, do nothing. Same exact problem, and guess what? Your linter will catch it. Right? If I did something like this on the command line, Emacs foo. Let's get rid of all this stuff. There we go. And if I use both my flags, oh no, don't tell me. Okay, GNU didn't want to do it. Let's C11. Good job, Clang. All right, Clang is just an alternative. You have that at the command line, by the way. Clang, WAL, foo. There we go. If you use a different compiler, then it has different error messages and different warnings. It has a different linter. It's actually catching this. And that's what REPL is using over here. It's using Clang instead. Right? What do you think Clang stands for? Not clanging a bell. It's the C language, right? Exactly. And so let's go ahead and run. We're caught in an infinite loop here. This program will never be done executing. Over here in an IDE like REPL here, I've got this stop button, right? And it stopped the process. What if I do the same thing over here from the command line? How do I stop that process now? You can close the terminal, kill everything. That's kind of overkill, though. So here's a tip, and the last tip for the day. If you are on Windows or if you're on a Mac, it doesn't matter. It's the same thing. I need to kill the current running process. So I will go Control-C to kill it. Right? This --C, that's how you read this. This is Control-C. So Control-C will kill an infinite loop, kill the program that's running, and then you can get control back over your shell here. Okay? You will write a program with an infinite loop at one point, I'm sure. So just remember how to kill the process. If you're in an IDE, there's probably a stop button somewhere. If you're on the command line, Control-C will kill the process.